I'm Ethan Buchman, co-founder of Cosmos. The other co-founder is here somewhere as well, which is kind of rare. He might be, there he is. You don't get us in the same room too often, so mad respect, Jay. Still love you, man. I'm also the CEO of Informal Systems. We do a lot of Cosmos dev, working on making the hub the best place to launch a chain. And we're also incubating Cycles. So I'm going to tell you a little bit about some of what we're building there that we think is going to be useful for the wider CosmWasm community. So what's Cycles? It's an open clearing protocol designed to clear the most debt for the most people with the least amount of money. You can check it out, cycles.money. Slowly, we're rolling out more and more information about it. Cycles is derived from our thinking about what's needed from a monetary perspective in order to take blockchains to the next level and really use them for what they're useful for, which in our mind is atomic multilateral settlement. But we're not going to talk too much about that. In order to make Cycles work, we need to do operations on encrypted data. And so this talk is really going to be about how we're doing that and why we chose the technology we happen to choose, and trying to rationalize that and lay out the framework we're building that we think that we've built for Cycles or are building for Cycles, but we think could actually be useful for everyone building CosmWasm applications to have privacy-preserving smart contracts. So I just want to give a shout out to two people in particular, Andrew Miller and Shoaib Ahmed, who work with us at Informal, who have been responsible for actually a lot of the work. So Andrew's been leading protocol design, and Shoaib is the main developer. I just ask dumb questions and test that things work, and then get to present about them. So lucky me, and of course the rest of the Informal Systems Cycles team. Okay, so what are we talking about? Private compute, right? Everyone is interested in this problem. ZK is blowing up, homomorphic encryption. This is something everyone's talking about. Privacy is a fundamental human right, and as blockchain developers, we've built all these powerful, decentralized, censorship-resistant systems, but they have almost no privacy anywhere, and it's a big problem, right? And so obviously there's been a lot of development. We have Zcash, Tornado Cash, we have Penumbra, Anoma, NIM in the Cosmos ecosystem, and others that are really interested in making this happen. But a lot of people will just turn to zero-knowledge proofs and say, okay, that's kind of all we need for cryptography, but it turns out, for privacy, but it turns out that's actually not enough. And so I want to kind of take you through an argument about these existing cryptographic primitives and why they actually won't work for us in Cycles and in many other applications. And to kind of spoil the outcome, we ultimately need trusted execution environments. And a big part of this talk is about, we got a hint about the power of SGX this morning from Dylan's talk on decentralized front ends. So this is kind of an extension of that. Okay, so let's talk about ZK. Everyone loves ZK. Everyone's heard about ZK. Everyone thinks ZK is all you need for privacy. It's not true. ZK only gives you privacy if you know all the inputs. Right? So if one individual has access to all the inputs, like when you're sending a shielded transaction in Zcash, there's only one user who has the data that has to be fed into producing the proof. They can get privacy because they don't have to reveal it with everyone else. So it works really well in that context. But if you want to do computations on global state, right, then whoever's producing the zero-knowledge proof has to have all the data. Right? And so that doesn't actually give you privacy in the world of kind of global compute, right? So it works really well when the individual who knows the data is the one who can produce the proof. But when you need to pool data across many users, you have this question of, well, who do we give all the data to produce the proof? And if we're willing to trust someone, then we can keep it private from everyone else. But that's not really a viable solution. So most of these things that call themselves ZK rollups, they face this problem, but they're really using ZK for succinctness, for proofs of integrity of computation rather than necessarily for privacy. And actually the original constructions for zero-knowledge proofs were about proving succinctly that a computation was done, and privacy almost came for free from the structure of the construction, which is kind of interesting. So ZK is really not enough. What we're trying to do in Cycles is we need to collect a large number of encrypted debts and then run a graph flow algorithm on them, right? So we want to get the entire network of debts, or at least a large network of debts from many different participants, and then run an algorithm on all of that to find cycles in the graph. And so ZK doesn't actually help us with that because someone needs to see all the data to run the algorithm, okay? What about multi-party computation? This actually does work. This gives us proper encrypted computation. No single agent can see all the data, right? You have some K of n agents, and as long as K of them are honest, this works, right? The problem here is that it's actually very expensive. It's very high network overhead, and there's a lot of work happening on it, but it's still not really usable for the kinds of large-scale computations we might want to do. And there's also this issue of collusion, right? You basically have to trust that these K nodes aren't going to collude, because if they do, they can decrypt everything, And even worse, they don't leave a trace, so it's not accountable. So you don't know if they're, if they've actually decrypted everything. Okay? So maybe you're thinking, okay, well, what about homomorphic encryption? Well, it turns out this is basically useless. Because in homomorphic encryption, you still have this problem of, well, who manages the decryption keys, right? Who actually gets to decrypt the thing? And so it's fine if you're just trying to outsource your compute, right? Then homomorphic encryption can allow you to take an untrusted machine, powerful machine, to do the compute for you and then give you back the result. But in a blockchain context, right, where everything is sort of running on chain, you still have this problem of who's going to decrypt, right? And so the way to think about homomorphic encryption here is that essentially allows you to take multi-party computation and swap the I/O overhead, the network overhead, for compute overhead, right? And so maybe it can make multi-party computation cheaper, but even if you use fully homomorphic encryption, you need MPC for managing the keys and the decryption, right? So some obligatory memes. Makara here has been memeing about this very actively over the last few weeks, so you should follow Bad Crypto Bitch on Twitter. That wasn't a swear word. I was just reading the alias here. So why not just use MPC? You get thrown out the building. FHE team shilling why they're better than MPC, but omitting details about how to split the decryption key, and so on and so forth, right? So this is important. So where's that leave us? It leaves us waiting for this stuff to be fast enough. ZK doesn't give us private compute. MPC is expensive, doesn't give us collusion resistance. FHE is expensive. In principle, it can make MPC cheaper. What's a practical solution that we can use today? I'm talking to Cosmos developers. You guys are practical people. You want things that work, that give us sufficient guarantees and that we can combine with other techniques as necessary. Yeah? In the infamous words of Amy Santiago, pick TEE dummies. Of course, if you do that, that would make you smart. So let's talk about TEEs, right? Private compute in trusted hardware. They're practical, they're fast. They give you an isolated enclave that means nobody can access the data in there, and you get proofs of correct execution by a particular binary. So you know that a particular code ran and gave you an output, and you can relatively easily just check a signature for all of that, right? Of course, the downside is they're vulnerable to potentially devastating side channel attacks, which is why everyone kind of got turned off of them some years ago, because there were all these attacks out there, and you have to trust the central issuer, right? Generally Intel, right? So Intel SGX is the most common popular version of a TEE. It's basically a set of instruction codes that extends the existing processor architecture. So it's not like there's a separate processor. It's your existing processor with extra opcodes, but then they do give you, hardware inscribed encrypted memory access. So part of your RAM gets sort of allocated to your enclaves. And that's what really the enclave is that encrypted memory. And in order to access it, you have to pass through these extra opcodes. And effectively, the operating system is treated as untrusted, right? And so the whole thing is secure from the host machine it's running on. And so even if you compromise the host, in principle, side channels aside, the only thing you can do is stop the thing from running, right? Now the side channels have been quite devastating historically. People have leaked, pretty much everything through them, and so that's something we need to deal with and take seriously. Intel talks about remote attestation. That's just their term for how you verify output from an enclave. So, inside the enclave, you produce a signature, and then you can verify that signature must have come from the trusted enclave. Okay, so how do we mitigate these vulnerabilities, these side channel issues? Well, actually, blockchains are perfect for this. They give us everything we need to do this and to lock down the TEE. What you do is you just require that execution within the enclave requires a round trip with the blockchain using a light client. So you effectively run a light client in your enclave as part of the binary that's going in there, and you have the blockchain, there's a setup process so that the blockchain is only going to work with something that knows there's a particular binary that's running in there, and it can thereby constrain what data that enclave can operate on and when it can operate and how it can operate, right? And many of the issues with side channel attacks just come from being able to replay execution in the enclave, right? If you can control the host and you can get the code to run over and over again, then you can detect side channels and try to make it leak. But if you stick a light client in there and you restrict it so that the binary will only run based on verification from the blockchain, and that it always requires this round trip, then you can knock out most of these potential attacks. And then, of course, you can go further and just produce zero-knowledge proofs of what you did in the enclave to get you, integrity and correctness without depending on the TEE, right? So the only thing you're going to end up depending on the TEE for is privacy over your global compute, right? But you can still use zero-knowledge proofs so that you did things correctly, and you can use this light client handshake thing to restrict how the enclave can run. Very powerful. So in some, you take your TE vulnerabilities, it's, they're leaking, and you slap a light client on it, and it fixes it. If you haven't actually watched this video for how flex tape, I watched it when I put together this meme. I was like, does this meme mean we actually fixed it, or is it like a Band-Aid solution? This stuff actually fixes the leak, okay? The guy like cuts a boat in half and then tapes it back together and then rides it. It's crazy. Watch the video, all right? So in summary, ultimately a complete design is actually going to combine everything. You're going to have FHE, MPC, ZKP, and TEE, right? Say it 10 times fast. Even with FHE and MPC and ZKP, you still benefit from adding a TEE to it because it prevents collusion and gives you sort of stronger guarantees and reporting on what actually happened and what ran. In the meantime, the TEs give us a very practical private compute and rapid prototyping environment that we can use today. We can reduce side channel attacks with blockchain protocol design, very practical, very useful, and we can add zero-knowledge proofs to reduce the dependency on the TE even further, right? So that's really only for privacy, right? And then, of course, we can do defense in depth. We can run multiple TEs, multiple types of ZKPs. Ultimately, ideally, we'd have open source hardware, and we'd have open source trusted execution. Right now we still kind of have to trust Intel's manufacturing process for this, but again, we're only going to trust it for the privacy. And I've even heard that they're looking to try to decentralize their key generation process. So we could get into all that. So one more meme from Makara here. While everyone's duking it out, TEs are making progress on important problems. Okay, so let's switch it up. So hopefully that sufficiently motivated and convinced you that actually TEs are viable. We should be using them. They've been overly fudded. Many of the historical issues have been addressed, and we can address them even further by using light clients. Use blockchains for what they're for. I have 5 minutes. That's not good. Forgot to set up a timer up here. And so now we can move forward with actually trying to use them to do privacy preserving contracts in CosmWasm, right? So many of you probably know about the Secret Network. Secret Network's great. It's a Cosmos chain. They run CosmWasm in SGX enclaves. In the Secret Network, everyone runs the SGX, right? So every validator, every node that joins the network, you have to do it because it's part of the global state, right? And that's led to certain issues because you can't restrict basically who runs the enclave, right? What we want to do is basically allow existing CosmWasm chains to add SGX functionality as a sidecar, where they can reduce the surface area by limiting who runs the enclave, when, and on what data, right? Rather than making it so that everyone has to run it, you can kind of reduce it, right? And so we're introducing Quartz, this SGX sidecar framework for CosmWasm, to allow you to add SGX contracts, private smart contracts, to any existing CosmWasm chain. So why a sidecar? Just to sort of quickly rehash, you can add it to any existing chain. You can limit who the operators are, right? So it doesn't have to be the entire validator set or every node. It could be selected from the validator sets. It could rotate. You could integrate with ABCI 2.0 or some of the work Skip's doing to select certain validators. You could just assign an individual party, multiple parties, however you want. And again, we aim to mitigate these SGX vulnerabilities via this light client control. So every execution has to go through a round trip with the blockchain. And one of the nice things about this is we can actually run arbitrary Rust code in the enclave. So it doesn't have to be, the code that's running isn't restricted to being written in CosmWasm. It could be, that could be like the out-of-the-box default structure, but you can actually run more optimized code. So you can rapidly prototype with TEs. You can add zero-knowledge proofs of many different kinds, as long as you can get a verifier in WASM. And maybe eventually you can add MPC or other techniques. So desired properties, again, we've kind of talked about a lot of this. We want this replay protection. That's what the light client proofs get. We want forward secrecy, so we want some way to rotate keys so that if things get compromised, and it won't be everything forever. It'll be sort of limited window. We want censorship resistance, and so anything users submit, we want it to be able to enter the enclave, and we want both strong and weak integrity. So we can get strong integrity through zero-knowledge proofs, weak integrity. We kind of made up these terms, but through remote attestation. So just to give you a quick overview, it's a very simple kind of design. We have a chain here with CosmWasm. Does this thing point? Oh, hell yeah. Users submit encrypted intents, encrypted to the public key of the enclave, which is registered on chain during a handshake process. I'll talk about it in a second. The intents are pulled down, decrypted in the enclave. Whatever compute you want is executed. The results are encrypted, published back on chain. The chain verifies the attestation from the enclave. It could verify a ZK proof as well, update whatever relevant state, and then the users can pull the encrypted results that matter to them. Okay. So there's definitely a lot of magic involved in building a good UX for all of this and making this all work. There's a lot of additional problems that come from everything being encrypted, but this is the sort of core flow. It's very, very straightforward. So I've been talking about this light client thing, so let me just go into it in a little bit more detail. We have both a handshake setup and a processing setup, right? So the handshake is sort of the initial thing to register the TEE, where basically you create a nonce and a key on the enclave, commit them to the contract, and then prove to the enclave they've been committed. And then every time the enclave runs, you increment the nonce. Right? And it's going to check what the nonce is on chain so that it knows it can only run with the latest nonce, so you can prevent it from from basically replay attacks, right? And then every time it goes to run, we have this processing handshake where the light client checks the contract state, only executes on the latest state with the incrementing nonce with all the data that it got there from the light client, right? And so this prevents it from executing on arbitrary data and allows the chain to completely control when and how the enclave runs and what it does. So I'll quickly just run through a few challenges that we had to sort of solve to get this working with CosmWasm chains that are split in half between proving the blockchain to the TEE and proving the TEE to the blockchain. So first, proving the blockchain to the TEE. One thing we needed was a stateless verifier for the Tendermint light client, essentially, right, for Common BFT, because we don't really want to reduce the surface area in the enclave. We don't want it making any syscalls. So we don't want it making network calls directly. So we sort of fetch the data, stick it in a file, and then hand it over to the enclave to actually do the verification. So we have a stateless light client verifier now for the Tendermint protocol that runs inside the enclave. The other thing we had to do that was kind of tricky is get Merkle proofs out of CosmWasm. It turns out, as far as we could tell, there wasn't any existing library for already doing that. So how do you do this? Well, you populate this query raw contract state request protobuf thing, and then you sacrifice a goat to the gods of Tendermint encoding. And if your sacrifice is accepted, then you will have the correct encoding, and then you will be able to make the appropriate ABCI query to get the Merkle proof out. So this is an example of the kind of goat you might want to sacrifice. I spent a few minutes finding one that wasn't too cute. Goats are very cute, and I don't want to murder baby goats. So we're still working on proofs for batch collection or batch proofs for collections from CosmWasm, but we have the basics of this working now. Going the other way, proving the TEE to the blockchain. The core thing is you need to be able to verify the signatures produced from the enclave. So Intel SGX has kind of two types of signature of remote attestation schemes, one called EPID, one called DCAP. EPID is the old mode where it actually required Intel to be online, and so it created even more dependence on Intel that made people really hate it. DCAP is the new one that actually significantly reduces the reliance on Intel, so everyone's kind of moving to that. Secret Network recently added DCAP support, but they did it through an SDK extension. And so a lot of the implementations would require a foreign function interface. So we're working on a pure Rust implementation that'll just run in existing CosmWasm, and we hope to have that ready soon. And then finally, ZK verifiers. RIS0 pretty much worked out of the box because you have verification in Rust, SP1 probably too. We were playing around with Noir. We really liked working with Noir, but there was no Rust verifier because they wrote it all in C++. So if you get the opportunity to talk to someone from Aztec, make sure to troll them because they make a big deal about writing everything in Rust, but turns out their entire ZK backend is in C++. And so let them know that the Cosmos kids know about that and are upset with them about it so that they do something sooner. So there's still a lot of work to do ahead of us. We have to clean things up a bit, document it before we actually publish it and make it available. So we hope to do that soon. But there's a lot of interesting stuff to make it all really production ready, forward secrecy, so key rotation, really managing state. So the cycles model is sort of stateless. You have a bunch of inputs, you run the graph algorithm, you get a bunch of outputs, but we want it to be able to work on stateful contracts as well. So you could run a DEX, a lending protocol, whatever you want kind of in this model. You could also run off-chain AI agents, things that couldn't even run on a blockchain in the first place. We want to support multiple kinds of solvers and solver decentralization and fault tolerance. So currently we've been focusing on just a single, sorry, by solver I mean the enclave host, just a single host. But obviously we want to be able to decentralize that, have multiple operators and decentralize things across them, and multiple verifiers of TEs and zero knowledge proofs. So that's pretty much it for me, and I hope I've managed to convince you that TEs are grossly underutilized and can be incredibly valuable, and we can mitigate a lot of the issues. Stay in touch. You can follow me on Twitter. You can follow Cycles Money on Twitter, and check out the website. Subscribe for the upcoming white paper and news on when we make things available. Thank you so much.
I'll start with a question. I didn't quite understand. What is the attack that the light client is solving? What can you do if you didn't have this light client?
If you didn't have it, then you could basically re-execute. You could get the enclave to rerun its binary, right? So the the way you mount these side channel attacks is you just run the same code on the same data or different kinds of data to kind of probe the thing and see if you can get it to leak information. And so if you as the host can control what's running on the enclave and when, then you can potentially spend as much time as you want like trying to extract data from it. But if there's a light client on it so that the blockchain controls when it runs, then even if you control the host, you can't force the enclave to run. It only runs based on things from the enclave, from the blockchain, yeah.
And then another question is that how do you solve this weak subjectivity problem in the Tendermint light client for initially bootstrap starting this SGX? Can't I just keep telling it, oh, this is a new Tendermint chain every time, and keep passing it the same data again and again?
Yeah, you need a trusted bootstrap for the light client, just like in any situation. But you would imagine that's being done by the developers who are deploying the contract in the first place, and then you'd want to keep it online so that you never have to reset it. Yeah.
So, who? I start a new SGX to start running this thing. Where am I getting? How do you tell the SGX which Tendermint light client to trust?
You have to initialize it, right? So
it has to be signed by a dev key or something.
Yeah, it will require some trusted initialization, just like every light client. Yeah.
Okay.
Yeah. That's a good question though. It's something I should have brought up. Yeah. Anything else?
Any other questions from anyone else?
Yeah. Oh, we got a mic for you.
I'm not super familiar with TEEs, but my understanding with the way they're typically used is not to necessarily offer end user privacy, but just privacy within an ecosystem that an organization controls. Is there something with DCAP that actually says that this code was in fact run on trusted execution environment from the user's perspective, so that they don't so that somebody is just simulating with private keys or something?
Yeah, ultimately there's a root of trust back to Intel that has a key that signs keys that are generated on the enclave that then produce signatures that you can verify, sort of similar to certificate authority infrastructure that tells you this thing was signed by your TLS connection was signed by Google, and you trust that because it was signed by some certificate authority. It's kind of the same thing, so that the fact that it goes back to Intel verifies that this actually came from an enclave. And when you boot up the enclave, it produces, they call them measurements, but basically a hash of the code that's running on the thing, right?
Interesting.
So the setup process, gives you the opportunity to make sure you know what code's running there, from a particular Git hash, produces a particular binary, so you're gonna want reproducible builds to make sure that you can verify that. And maybe when you first deploy it, you want some voting process or devs to sign off on it to be okay, we know the right binary is running on this thing, this is its hash, and then any future remote attestation will prove to you that, will sign over the fact that that code is what was running there with that hash.
Okay.
Yeah.
And then lastly, just best places to learn more.
About SGX?
SGX. Is it, Secret and SGX is the best place to look to learn more about TE and a blockchain environment? Yeah,
there's scattered resources. We can put something together. Andrew's been keeping a Notion page that lists some good resources, but we'll link to that.
Awesome.
Yeah.
Questions?
Great talk.
Thank you.
Sorry. You mentioned that you guys are kind of going through some lengths to make sure that you can have a ZKP for the execution within the TE, but it sounds like you also had all sorts of guarantees about the particular code hash and things like that. So I'm just curious, what are you getting out of the ZKP that
You're just reducing how much you have to trust Intel.
Okay.
That's it. So if you have problems with that, it feels a little bit easier to trust them for privacy than for money movement, correctness of an execution, right? And so if you're really worried about that kind of thing, then if Intel is compromised, then the worst thing that happens is a privacy leak rather than some kind of incorrect state or something like that.
Yeah.
But if you're comfortable with it, you could totally just use the remote attestation, and then you don't need zero knowledge proofs at all. Yeah.
I see.
But we'd recommend. They're getting so much faster and better. You might as well try to get what you can out of them. Yeah. Yeah.
Cool. Thank you.
Yep. Thank you.
Quick question. Does ARM have something similar to TE?
I don't know. Do they? Does someone know? So you can't remote attest? Yeah. Okay.
Any other questions? I saw some more hands, I thought. I guess one is, you mentioned like doing it through CosmWasm because you were trying to avoid, like, you just said like in the SDK there's like FFI interfaces you have to go through, but there's also like FFI interfaces in CosmWasm. Like, wouldn't it be like, can we make it so we can access it to through the Cosmos SDK? Because I think one of the most useful places to use this would be in something like Skip API, Block SDK.
We could, yeah. We could make it work wherever we want, yeah. Totally. We just thought it would be, it might be most useful if we try to make it work out of the box without anyone having to upgrade. And we don't have it like fully there yet, but I'm expecting we'll be able to because it's just I think it's just a SecP 256R1 signature, which if I understand is supported now and everything. So, but if we want it, natively in the SDK or in other places, we could do that too, yeah.
Cool. All right. All right, thank you.
Awesome, thanks guys.